As I begin this journey with you, I want to introduce myself in the way I often speak when sharing the wonders of the universe, because my name is Michio Kaku, and throughout my life as a physicist, my mission has been to explore the deepest mysteries of space, time, matter, and the laws that govern our reality. And in the year 2025, I feel as though the world of physics has opened a new doorway, revealing discoveries that challenge our imagination and expand our understanding of the cosmos. And today, I want to guide you through some of the most extraordinary breakthroughs achieved this year, explaining them in simple language so that anyone, no matter their background, can feel the same curiosity and excitement that scientists feel when they uncover something truly revolutionary. And with that brief introduction, let me begin with one of the most fascinating discoveries of 2025, something astronomers have come to call the little red dots, mysterious compact objects found in the distant universe that have captured the attention of researchers everywhere. And as I explain this, I want you to imagine me narrating gently while standing beside a large screen displaying deep space telescope images, pointing toward faint crimson specks scattered across the darkness of space. Because these little red dots are not ordinary stars or familiar galaxies, but rather tiny, extremely dense, reddish structures that seem to exist billions of years in the past, during a time when the universe was still very young. And what makes them so astonishing is that despite their small size, they appear to contain an unexpectedly large amount of mass and star-forming material, almost as if entire galaxies were compressed into tiny cosmic seeds. And as I speak, I tell the audience that this discovery forces us to rethink how galaxies formed in the early universe, because for many years, scientists believed that galaxies grew slowly, building themselves up over long periods of time through gradual accumulation of gas, dust, and stars. Yet when we observe these compact red objects from 2025 survey data, we see evidence that some galaxies may have formed much faster and more violently than previously imagined, almost like intense cosmic firestorms rapidly shaping enormous structures in a fraction of cosmic time. And I continue by saying that some researchers think these little red dots might be the precursors of massive elliptical galaxies we see today, meaning that what we are observing could be the childhood phase of galaxies that later evolved into gigantic, calm structures over billions of years, while others suggest an even more dramatic explanation, proposing that hidden supermassive black holes may be buried inside some of these objects, compressing matter and radiating energy in ways that make them appear red, compact, and mysterious to our instruments. And I explain in simple terms that when we look far into the universe, we are actually looking back in time. So these red dots are like archaeological relics from the dawn of galaxy formation, frozen snapshots of the universe's turbulent youth. And studying them allows us to test our theories about how gravity, dark matter, and cosmic gas interacted in the earliest eras of creation. And I tell the audience that 2025 has been especially important because new telescope instruments and data analysis techniques finally gave scientists the clarity needed to examine these objects in greater detail, revealing their structure, temperature, and composition more accurately than ever before. And as I describe this, I emphasize that discoveries like this are not just isolated findings, but part of a much larger scientific story. Because every time we uncover something unexpected in the universe, it forces us to question what we thought we knew, refine our models, and sometimes even rewrite the textbooks. And that is exactly what is happening right now with the little red dots, as astronomers around the world debate their origin, their mass, their role in cosmic evolution, and what they imply about the speed and intensity of star formation in the early universe. And I tell the viewer that one of the most beautiful aspects of science is that uncertainty is not a weakness, but a sign of discovery. Because when we find something we cannot fully explain, it means we have reached the frontier of knowledge, standing at the edge of the known world, ready to push forward into new territory. And that is exactly what this 2025 discovery places us, at a moment when our instruments show us something real, yet our theories must evolve to make sense of it. And as I continue narrating in the same continuous flow, I invite the audience to imagine how scientists across observatories, universities, and research centers are now working together, comparing data, running simulations, and testing hypotheses, trying to determine whether these compact galaxies formed through rapid gravitational collapse, intense bursts of star formation, or interactions with powerful central black holes. And I remind them that even though these objects appear small in images, the physics behind them is enormous, involving colossal gravitational forces, extreme densities, and the chaotic environment of the early universe, when everything was hotter, denser, and more dynamic than the cosmos we see today. And I say that in many ways, studying the little red dots is like studying the childhood memories of the universe itself, because they reveal how structure first emerged from cosmic chaos, how matter gathered, how stars ignited, and how the early universe transitioned from a dark, formless void into a complex cosmic tapestry filled with galaxies, stars, and planets, including, eventually, the world we live on today. And as I begin slowly preparing to transition toward the next major breakthrough of 2025, I tell the audience that discoveries like this remind us that even after decades of observation and theory, the universe remains full of surprises, full of hidden stories waiting to be uncovered, and that every new observation deepens our understanding of where we came from and how the cosmos has evolved across billions of years. And with that thought in mind, I gently guide the narrative forward, saying that while the little red dots reveal secrets about the early universe, another discovery from 2025 challenges something even more fundamental, something that affects the fate of the entire cosmos itself. And that is the question of whether dark energy, the mysterious force driving the expansion of the universe, may actually be weakening over time. And I prepare to explore that extraordinary idea as the next chapter in our journey through the breakthroughs of this remarkable year. As we move from the distant galaxies of the little red dots to the very fabric of the universe itself, I want to discuss one of the most profound discoveries of 2025, a revelation that challenges our understanding of the cosmos at the largest scale. And that is the accumulating evidence that dark energy, the mysterious force responsible for accelerating the expansion of the universe, may not be as constant as we once believed. And as I explain this, I want you to picture the universe as a vast, stretching balloon, where galaxies are like tiny specks on the surface, moving apart as the balloon inflates, driven by the invisible pressure of dark energy. And for decades, physicists have assumed that this dark energy is uniform and unchanging, a constant property of space itself. But in 2025, new observations from advanced telescopes and large-scale cosmological surveys provided tantalizing hints that this assumption may not be entirely correct. And as I narrate in my first-person voice, I tell the audience that scientists carefully analyzed light from distant supernovae, galaxies, and cosmic background radiation, tracing how the rate of expansion has changed over billions of years, and they discovered subtle variations suggesting that the strength of dark energy could be slowly diminishing, a phenomenon that would have profound implications for the ultimate fate of the universe. And I explain in simple yet cinematic terms that if dark energy weakens over time, the universe may not expand forever at an accelerating pace, as previous models predicted, but instead could enter a phase where the expansion slows, potentially allowing gravity to regain influence over cosmic structures, a possibility that could radically alter long-term predictions about cosmic evolution. And I emphasize that such a shift would transform our understanding of fundamental physics because it suggests that the laws governing the universe may be dynamic and change over cosmic time rather than fixed. And as I continue speaking, I guide the audience to consider what this means for humanity's understanding of existence, explaining that dark energy is intimately tied to the geometry of space-time itself, influencing everything from the formation of galaxies to the distribution of cosmic matter and the evolution of clusters of galaxies across billions of light years. And I tell the viewers that in 2025, this discovery generated heated debates among theorists and observational astronomers alike because it challenges the core assumption that the universe's expansion is controlled by a static, unchanging force. And I continue by using an analogy to make it tangible. Imagine pushing a cart with a steadily weakening engine. At first, it speeds up, but gradually the influence of the initial push diminishes, and eventually other forces like friction or gravity begin to dominate. And in a similar way, a weakening dark energy would allow gravity to regain some control over the expansion of the universe, possibly influencing the distribution of matter and the growth of large-scale cosmic structures. And I tell the audience that while this may sound abstract, it is extraordinarily concrete in the sense that it will determine the ultimate fate of all galaxies, stars, and planets, including our own. And as I explain further, I remind viewers that the tools enabling this discovery were monumental, including next-generation space telescopes with unprecedented sensitivity, wide-field ground-based surveys mapping billions of galaxies, and sophisticated computational models simulating billions of years of cosmic evolution. And together, these advances allowed scientists to detect the tiny deviations in expansion rates that indicate dark energy may not be constant. And as I speak, I emphasize that detecting such subtle differences is like measuring the growth of a human hair from thousands of kilometers away, a feat of precision that requires ingenuity, patience, and global collaboration. And I expand on the significance by saying that if confirmed, a weakening dark energy would not only rewrite our predictions of the universe's destiny, but would also challenge theoretical frameworks such as Einstein's general relativity, quantum field theory, and our understanding of vacuum energy, because it suggests that the energy content of empty space may vary over time in ways that are currently unimaginable. And I explain that theorists are now exploring a variety of models, from quintessence fields to dynamic vacuum energy, each attempting to explain why the push of dark energy might change. And I describe these in simple terms, comparing them to invisible cosmic winds that shift strength over eons, gently pushing galaxies apart at different rates, sometimes faster, sometimes slower, depending on conditions in the cosmic landscape. And I highlight that 2025 was critical because these hints, while preliminary, are supported by multiple independent data sets, reducing the possibility of observational error and giving scientists real confidence that something remarkable is happening on the largest scales of space and time. And as I continue, I make it clear to the audience that this is not merely academic speculation, but a profound inquiry into the nature of reality itself, because the behavior of dark energy controls whether the universe ends in a cold, eternal expansion, a big freeze, or perhaps in some as yet unimagined cosmic fate. And I tell viewers that understanding it could even inform other mysteries, such as the evolution of dark matter, the formation of supermassive black holes, and the distribution of galaxies across the cosmic web. And I explain that the weakening of dark energy, if verified, might hint at new physics beyond our current standard models, pointing toward new interactions, particles, or forces that shape the universe at the most fundamental level. And as I continue this narrative, I describe the international collaboration involved, with astronomers from observatories in Chile, Hawaii, and space-based telescopes combining their data sets, employing machine learning and advanced statistical techniques to isolate the faintest signals, all of which demonstrates the power of global science in pushing the boundaries of knowledge. And I remind the audience that while this discovery is still unfolding, it marks one of the most exciting areas of physics in 2025 because it has the potential to answer the question humanity has asked for centuries. What will become of the universe itself? And as I speak, I weave in an accessible analogy, saying that if we imagine the universe as a vast ocean, then dark energy is the wind propelling the waves outward. And in 2025, it appears that the wind may be gradually losing force, subtly changing the motion of everything on the surface, from the tiniest ripples to the largest swells. And understanding that shift is essential to predicting the ocean's future. And I conclude this segment by telling viewers that while the universe may seem incomprehensibly vast, every new measurement, every new observation, every new discovery brings us closer to understanding the rules that govern it, and that the 2025 breakthroughs in dark energy studies represent a monumental step in that journey, reminding us that even the invisible, the seemingly constant, may evolve over time, and that the universe is far more dynamic, mysterious, and beautiful than we ever imagined, setting the stage perfectly for the next discovery we will explore, the deep geophysics of Earth's core, which brings us from the cosmic scale back to our home planet, revealing secrets hidden beneath our feet that are just as astonishing in their own right. Shifting our focus from the vastness of the cosmos back to our own planet, in 2025, scientists made remarkable progress in understanding the deep geophysics of Earth's core, revealing complexities and dynamics that had remained hidden for decades. And as I explain this, I want you to imagine descending through thousands of kilometers of rock and molten metal, traveling past the crust, the mantle, and the outer core, into the heart of our planet, where a solid inner core of iron and nickel spins, surrounded by a turbulent liquid outer core. And what researchers discovered this year is that the inner core is not as simple or uniform as we once thought, but instead exhibits subtle variations in rotation and crystalline structure that have profound implications for our understanding of planetary physics. And I tell the audience that by analyzing seismic waves generated by earthquakes and artificial sources, scientists were able to detect minute differences in how these waves travel through the core, revealing that parts of the inner core may rotate slightly faster or slower than the planet's surface, a phenomenon known as differential rotation. And I explain in simple language that this is akin to the blades of a slow-moving fan spinning at different speeds, depending on their location, producing complex patterns that influence the magnetic field generated by the geodynamo in the outer core. And as I continue, I describe how these 2025 findings indicate that the inner core may contain distinct crystalline regions or patches that interact with the liquid outer core in ways that we are only beginning to understand, affecting not only the magnetic field, but also the heat transfer, convective flows, and even the long-term evolution of Earth's rotation.
And I emphasize that this is important because the Earth's magnetic field protects life on the surface from harmful cosmic radiation and solar wind, meaning that these inner core dynamics are critical to maintaining a habitable planet. And I guide the audience through the conceptual leap, explaining that although these processes occur thousands of kilometers below our feet, they have observable consequences on the surface, from fluctuations in geomagnetic strength to variations in tectonic activity and even subtle influences on the length of a day. And as I narrate in first-person voice, I remind viewers that these measurements are extraordinary feats of precision, requiring highly sensitive seismometers, sophisticated modeling techniques, and decades of data to isolate the tiny signals from the constant background noise of the planet. And in 2025, the combination of new global seismic networks and advances in computational simulation allowed researchers to create three-dimensional maps of the inner core's structure, offering an unprecedented glimpse into Earth's hidden interior. And I explain that the findings suggest the inner core is more heterogeneous than previously believed, with regions that may be slightly softer, denser, or oriented differently in terms of crystalline alignment. And these variations may influence how heat flows from the core to the mantle, a process that drives mantle convection, volcanism, and plate tectonics, which in turn shape the landscapes, climates, and even the distribution of life on Earth. And as I continue speaking, I tell the audience that the 2025 discoveries also hint at long-term changes in the inner core's rotation rate, which could affect the geomagnetic field over decades and centuries, meaning that understanding these processes is not just an academic exercise, but a practical one, with implications for navigation, satellite communication, and power grids that depend on a stable magnetic environment. And I provide a simple analogy, saying that the Earth's core is like the engine of a vast planetary machine, and any subtle shifts in its operation ripple outward, influencing every aspect of life on the surface. And I describe how the research teams in 2025 combined seismic tomography, laboratory experiments on iron at extreme pressures, and sophisticated fluid dynamics models to simulate how the inner and outer cores interact, revealing complex behaviors such as superrotation, localized anisotropies, and even wave-like motions similar to ocean currents within the molten metal. And I explain in accessible terms that these phenomena, though invisible to our eyes, are fundamental to the planet's stability, affecting not only the magnetic field, but also the dynamic processes that have allowed life to persist for billions of years. And I narrate that 2025 marked a breakthrough because these subtle inner core variations were measured with a precision previously thought impossible, allowing scientists to test long-standing theories about the geodynamo and core evolution. And I emphasize that this achievement represents decades of cumulative effort, combining advances in seismology, mineral physics, high-performance computing, and collaborative international research. And as I continue without pause, I remind viewers that Earth,
often taken for granted in its seeming stability, is in fact a dynamic, evolving planet with processes deep within its core that are just as mysterious and fascinating as the most distant galaxies. And I expand on this idea by saying that understanding Earth's core is also essential for comparative planetology, because by learning how our planet works, we can better understand other rocky planets, their magnetic fields, their tectonics, and their potential for habitability. And I point out that in 2025, these findings have energized research in exoplanetary science as well, as scientists now apply models of core dynamics to planets beyond our solar system, trying to infer their internal structures and magnetic environments based on mass, radius, and rotational data. And I explain that this interplay between deep Earth studies and cosmic exploration highlights a recurring theme in modern physics. The same principles govern matter from the scale of atoms to the scale of planets and galaxies, and discoveries in one domain often illuminate mysteries in another. And I continue to weave this narrative by telling the audience that as we peer into the inner core, we are reminded of the elegance of physical laws, because the interactions of molten metals and spinning solids at extreme pressures obey predictable physics, yet produce extraordinarily complex and beautiful behavior, much like the turbulence of a river or the swirls of clouds in the sky. And I conclude this segment by emphasizing that the geophysics breakthroughs of 2025 are monumental not only for their scientific insight, but also for their practical impact, because they enhance our ability to predict geomagnetic reversals, understand the long-term stability of the planet, and ultimately appreciate the deep, invisible forces that make life on Earth possible. And as I transition toward the next topic, I prepare the audience to shift from the inner workings of our planet to the quantum world and the remarkable discoveries of 2025 that earned global recognition through Nobel-level physics, discoveries that illuminate the behavior of matter at its most fundamental level and bring us closer to the quantum technologies that will shape the future, continuing the story of human curiosity, ingenuity, and the endless quest to understand the universe at every scale, from the depths of Earth's core to the furthest reaches of space. As we move from the deep interior of our planet to the cutting edge of human ingenuity, 2025 has been a remarkable year for Nobel Prize-level physics, where some of the most profound and groundbreaking work was recognized, highlighting discoveries that not only deepen our understanding of the universe, but also provide practical applications in quantum technology. And as I explain this, I want you to imagine me speaking in my first-person voice, standing before a grand lecture hall, addressing an audience of curious minds, describing how this year scientists achieved breakthroughs in understanding macroscopic quantum phenomena, particularly in superconducting systems and quantum circuits, and these discoveries were so transformative that they earned the highest honors in physics, emphasizing the profound implications for both theory and practical technology. And I tell the viewers that what makes these achievements extraordinary is that they demonstrate quantum effects at scales much larger than the atom, allowing researchers to control, manipulate, and observe quantum states in systems that are large enough to engineer. And as I continue, I explain in simple language that in the past, quantum behavior was mostly confined to the microscopic world, electrons, atoms, and photons. But in 2025, researchers demonstrated that entire circuits composed of billions of atoms could exhibit coherent quantum behavior, where phenomena like superposition and entanglement could be reliably generated and measured, opening the door to the next generation of quantum computers, sensors, and communication devices. And I provide an analogy to make this tangible for the audience, saying that it is as if entire musical orchestras, rather than single instruments, could play in perfect quantum harmony, producing effects that are both delicate and precisely controlled, a feat unimaginable just a decade ago. And I narrate that these breakthroughs also have critical implications for quantum error correction, the technology that allows quantum computers to maintain stability despite interference. And in 2025, new methods for stabilizing qubits were demonstrated, improving coherence times and allowing for more complex computations to be performed. And I explain that this represents a major step toward realizing practical quantum machines capable of solving problems that classical computers cannot, including simulating complex molecules, modeling climate systems, and optimizing vast networks. And I continue by highlighting the Nobel recognition itself, explaining that the prize this year acknowledged not only the experimental feats, but also the theoretical understanding required to interpret these results, linking quantum mechanics with electrical engineering and material science in ways that bridged decades of research. And I tell the audience that this recognition also underscores a broader theme in modern physics:
the interplay between fundamental theory and technology, where discoveries in one domain rapidly inform and accelerate progress in the other. And I explain further that in 2025, teams of scientists used these quantum circuits to explore phenomena previously thought to be purely theoretical, including macroscopic tunneling, quantum coherence in large systems, and entanglement across multiple qubits. And I emphasize to the audience that these experiments are not only remarkable demonstrations of human skill and precision, but also critical tests of the very foundations of quantum mechanics, because by observing how these large-scale systems behave, we gain insight into the limits of quantum theory and the boundary between the quantum and classical worlds. And as I continue narrating, I describe in cinematic terms the environment of these experiments: cryogenic laboratories where temperatures near absolute zero reduce thermal noise, high-tech shielding to isolate the systems from electromagnetic interference, and arrays of superconducting circuits delicately manipulated by lasers and microwaves, all working in harmony to maintain fragile quantum states. And I explain that such precision is necessary because any disturbance can collapse the quantum states, much like a delicate soap bubble popping at the slightest touch. And yet, in 2025, researchers succeeded in reliably creating and sustaining these states long enough to perform meaningful operations, a feat that had eluded scientists for decades. And I expand on the significance by saying that these advances are not just technical achievements, but foundational for a future where quantum technologies transform computation, encryption, communication, and even sensing in ways that will touch everyday life, from unbreakable secure networks to revolutionary medical imaging techniques and advanced simulations of complex systems. And I narrate that the 2025 breakthroughs also include novel materials and fabrication techniques that allow these circuits to be scaled up, combining advances in nanotechnology, superconductivity, and photonics to create devices that are not only functional but robust and reproducible, which is a prerequisite for commercial and industrial applications. And I tell the audience that these Nobel-level accomplishments represent a convergence of decades of work in quantum theory, experimental physics, and engineering, culminating in results that demonstrate how human curiosity and ingenuity can unlock phenomena that were once considered purely theoretical. And I continue by explaining that the recognition of these achievements also inspires the next generation of scientists, showing that even the most abstract theories can have real-world impact, and that perseverance, creativity, and collaboration are essential to pushing the boundaries of knowledge. And as I weave this narrative forward,
I remind viewers that the 2025 Nobel-level discoveries are deeply connected to other breakthroughs we have discussed, from cosmology to condensed matter, because they all rely on a deep understanding of the fundamental laws of nature. And I described that the precision required for these experiments echoes the precision in measuring dark energy or mapping the inner core of Earth, highlighting the interconnectedness of physics at all scales. And as I continue seamlessly, I emphasize that the 2025 achievements in quantum physics demonstrate that we are entering an era where the strange, counterintuitive properties of the quantum world are no longer confined to the laboratory, but are poised to become practical tools that will redefine technology, computation, and even our conception of reality itself. And I narrate that these breakthroughs also raise profound philosophical questions, reminding us that quantum mechanics governs not only the behavior of particles, but the possibilities of the universe, and that by harnessing these principles, we are learning to navigate a world where probability, superposition, and entanglement are tangible and measurable. And I close this segment by telling the audience that the Nobel-recognized discoveries of 2025 are milestones in human understanding, showing that the boundaries between theory and experiment, the abstract and the applied, are being crossed in ways that will influence science, technology, and society for decades to come. And as we prepare to move from the microscopic quantum world back to the cosmic scale, we can see the continuity of human curiosity, linking our quest to understand the deepest laws of matter with our efforts to listen to the vibrations of space-time through gravitational waves, the next extraordinary topic in our exploration of 2025 physics breakthroughs. Turning once again to the vastness of the cosmos, 2025 was a landmark year in astrophysics and gravitational wave research, where scientists captured some of the most detailed and powerful cosmic signals ever observed, providing unprecedented insights into the most violent and energetic events in the universe. And as I explain this in my first-person narration, I want you to imagine me guiding the audience through a cinematic journey of space-time, describing how colliding black holes and neutron stars send ripples across the fabric of the universe, ripples that we call gravitational waves. And these waves, although imperceptible to the human senses, carry information about the masses, spins, and trajectories of their cataclysmic sources, allowing us to listen to the universe in a way that complements the visual data collected by traditional telescopes. And I tell the audience that in 2025, improvements in detector sensitivity, including upgrades to facilities such as LIGO, Virgo, and Kagra, enabled the detection of signals that were fainter, more complex, and distant than ever before, allowing scientists to observe not just collisions of stellar mass black holes, but also mergers involving intermediate mass black holes and neutron stars with unprecedented clarity. And I explain in simple language that each gravitational wave event is like a fingerprint of the extreme physics occurring in these cosmic laboratories, revealing how matter and energy behave under conditions impossible to reproduce on Earth. And as I continue, I describe that one of the most exciting aspects of 2025's discoveries is that these waves provide direct evidence of Einstein's general relativity at its most extreme, confirming predictions about space-time curvature, the energy emitted during massive mergers, and even subtle effects such as precession and frame dragging. and I narrate that scientists were able to reconstruct the waveforms of multiple events, mapping the in-spiral, merger, and ring-down phases with incredible precision, which allows them to estimate the masses and spins of black holes and neutron stars, and even infer the nature of matter inside neutron stars, which remains one of the biggest mysteries in astrophysics. And I explain that understanding neutron star collisions is crucial because they are the primary factories for heavy elements like gold and platinum, meaning that gravitational wave observations not only illuminate extreme physics, but also help explain the origin of the elements that make up planets and even ourselves. And as I continue, I tell viewers that 2025 also saw the observation of multi-messenger events, where gravitational waves were accompanied by electromagnetic signals, such as gamma-ray bursts or visible light, allowing astronomers to pinpoint the location of these cataclysms and study their aftermath in exquisite detail. And I narrate that these multi-messenger observations mark a new era in astronomy, where different types of signals are combined to build a more complete picture of cosmic phenomena. And I explain that this holistic approach allows scientists to probe questions about the rate of expansion of the universe, the behavior of matter at nuclear densities, and even tests of fundamental physics under extreme conditions. And I emphasize that gravitational wave astronomy in 2025 is not just about observing individual events, but about constructing a statistical map of the universe, showing how black holes form, merge, and evolve over cosmic time, and providing clues to the population of compact objects that exist throughout the cosmos. And I narrate that the technological innovations enabling these breakthroughs are themselves remarkable, including the use of laser interferometry at unprecedented sensitivities, vibration isolation systems that cancel out seismic noise, and sophisticated data analysis algorithms capable of teasing signals from vast amounts of background noise. And I explain to the audience that the precision required is staggering, because the distortions in space-time caused by gravitational waves are smaller than 1,000th of the diameter of a proton, yet scientists can detect and interpret them, revealing phenomena occurring billions of light-years away. And I continue by describing the broader implications, saying that gravitational waves are now becoming a tool for cosmology, providing independent measurements of the Hubble constant, constraints on dark energy, and tests of alternative theories of gravity. And I tell viewers that each detection adds to a growing library of cosmic events, allowing theorists and observers to refine models of star formation, binary evolution, and the life cycle of compact objects. And as I narrate further, I emphasize that 2025's breakthroughs also include the detection of rare events such as black hole neutron star mergers, which are key to understanding tidal disruption, matter ejection, and the production of heavy elements. And these observations were only possible due to international collaboration, continuous monitoring, and advances in machine learning algorithms capable of recognizing subtle patterns in noisy data. And I explain that this collaborative effort, uniting physicists, astronomers, engineers, and computer scientists, reflects the global nature of modern science, where understanding the universe is a collective endeavor. And I continue seamlessly, saying that the discoveries of 2025 reinforce the concept that we live in a universe of extremes, where black holes thousands of times the mass of our sun can dance and collide, where neutron stars can pack a sun's mass into a sphere barely 20 kilometers wide, and where the fabric of space-time itself quivers in response to these events.
And I narrate that by detecting and analyzing these waves, we are not only testing the limits of physics, but also creating a new language to communicate with the universe, a language of vibrations, frequencies, and amplitudes. And I tell viewers that these advances bring humanity closer to answering some of the oldest questions in science. How do black holes form? How do stars die? How is matter recycled in the cosmos? And even, what is the ultimate fate of the universe itself? And as I continue, I describe that gravitational wave observations in 2025 have begun to uncover patterns in the population of black holes, suggesting that intermediate mass black holes, previously speculative, may be more common than expected, and that the spins and orientations of merging black holes provide clues to their formation channels, whether from isolated binaries or dense stellar environments. And I narrate that every new detection sharpens our understanding, allowing physicists to test competing models, probe general relativity under extreme conditions, and even search for evidence of exotic objects such as primordial black holes, boson stars, or modifications to Einsteinian gravity.
And I conclude this segment by telling the audience that the astrophysics breakthroughs of 2025, especially in gravitational wave detection, represent a monumental step in humanity's ability to observe and understand the universe, transforming abstract equations into tangible, measurable phenomena, expanding our cosmic awareness and reminding us that the universe is alive with motion, energy, and forces far beyond what we can see, and that through these discoveries we are learning not only about distant black holes and neutron stars, but also about our place in the cosmos and the fundamental laws that govern everything from the smallest particles to the largest structures in existence, setting the stage perfectly for the final segment of our journey, the remarkable advances in new materials and condensed matter physics that also defined 2025 as a truly revolutionary year for physics. As we shift our focus from the cosmos back to the tangible world around us, 2025 has also been a groundbreaking year in the field of new materials and condensed matter physics, where researchers have achieved extraordinary progress in understanding and engineering materials at the atomic and molecular scale, unlocking properties that were previously thought impossible and paving the way for transformative technologies. And as I explain this in my first-person narration, I want you to imagine laboratories filled with ultra-clean environments, advanced microscopes capable of resolving individual atoms, and scientists delicately manipulating ultra-thin layers of metals and crystals with precision almost akin to an artist crafting a masterpiece. Because the advances of 2025 are not merely incremental, they represent a leap in our ability to control matter itself. And I tell the audience that one of the most exciting developments has been the fabrication and study of two-dimensional materials, ultra-thin sheets only a few atoms thick, which exhibit electrical, optical, and mechanical properties far beyond what conventional bulk materials can achieve. And I explain that by stacking, twisting, or combining these layers in precise arrangements, scientists have discovered novel quantum behaviors, including superconductivity at higher temperatures, unusual magnetic phenomena, and exotic phases of matter that behave in ways never seen before. And I continue by saying that these breakthroughs are not purely academic, because understanding and harnessing these materials could revolutionize electronics, energy storage, quantum computing, and even wearable and flexible technologies, allowing devices that are faster, lighter, more efficient, and capable of entirely new functions. And as I speak, I describe that researchers in 2025 successfully engineered materials in which electrons flow without resistance under conditions that were previously unattainable, a feat that may dramatically reduce energy loss in electronic systems. And I explain in simple language that this is akin to creating a frictionless highway for electrons, where energy can move efficiently without being wasted as heat, with enormous implications for global energy consumption and technology development. And I continue narrating that beyond superconductivity, condensed matter physicists have uncovered new behaviors in quantum crystals and layered topological materials, observing phenomena such as fractional charge carriers, edge currents protected from disorder, and tunable quantum phases, which not only deepen our fundamental understanding of quantum mechanics, but also provide practical pathways to robust quantum devices. And I tell the audience that these materials are being designed with atomic-level precision, where the arrangement of each atom can be controlled to produce desired electronic, magnetic, or optical properties, allowing scientists to program matter, much like we program computers.
In 2025, experiments showed that even subtle manipulations, such as twisting one layer relative to another by a fraction of a degree, can dramatically change the material's behavior, turning an insulator into a superconductor or inducing novel electronic states. And this remarkable control has led to the discovery of entirely new phases of matter that challenge existing theories, providing fertile ground for both fundamental physics and technological innovation. As I continue in my cinematic first-person voice, I emphasize that condensed matter physics is not just about the microscopic. It connects directly to the macroscopic world, shaping the devices we use, the energy systems we rely on, and the computational technologies that will define our future. And I describe that in 2025, collaborations between experimentalists and theorists allowed researchers to model and predict behaviors in these complex materials with unprecedented accuracy, using high-performance computing, advanced simulations, and AI-assisted design, which accelerates discovery and allows scientists to explore a vast landscape of possible materials that might have never been tested otherwise. And I tell viewers that the implications extend beyond electronics, because understanding quantum materials also informs the development of sensors capable of detecting minute magnetic, electric, or gravitational signals, leading to innovations in medical imaging, navigation, and environmental monitoring. And I narrate that this interplay between fundamental understanding and practical application is a recurring theme in 2025 physics, linking breakthroughs in condensed matter physics to advances in quantum computing, energy storage, and even astrophysical instrumentation. And I explain that the ability to engineer materials at the atomic level also allows scientists to explore emergent phenomena, collective behaviors that arise when many particles interact in complex ways, producing unexpected properties such as high-temperature superconductivity, topological order, or quantum entanglement across macroscopic scales. And I continue by emphasizing that these discoveries are not isolated, but part of a global effort in 2025 that combines physics, chemistry, materials science, and engineering, demonstrating how interdisciplinary research can accelerate progress and enable outcomes that were once considered purely theoretical. And I tell the audience that the year 2025 also saw progress in understanding exotic metallic alloys, layered van der Waals structures, and cryogenic quantum crystals, revealing behaviors that challenge conventional condensed matter theory. And I describe in simple terms that by probing how electrons, phonons, and spins interact in these materials, scientists gain insight into fundamental forces and correlations that govern matter itself,
insights that may one day be applied to develop superconductors operating at room temperature, ultra-efficient batteries, and novel quantum sensors. And I continue smoothly saying that condensed matter physics connects directly to our everyday lives, even if the phenomena are hidden at the nanoscale, because the principles learned here are foundational for next-generation electronics, energy-efficient systems, and technologies that will redefine computing, communication, and medical devices. And I narrate that 2025 has demonstrated that controlling matter at this level is not science fiction, but tangible reality, with carefully engineered structures revealing entirely new behaviors and guiding us toward applications that will transform society. And as I speak, I remind viewers that these advances also deepen our understanding of quantum mechanics, phase transitions, and emergent phenomena, showing that even at the smallest scales, nature is capable of extraordinary complexity. And I continue by saying that the discoveries of 2025 in new materials are a bridge between fundamental physics and applied technology, where understanding the rules of matter allows us to design tools, devices, and systems that were unimaginable just a few years ago. And I narrate that the excitement in laboratories is palpable because each new experiment, each new material synthesized brings the possibility of novel phenomena and transformative applications. And I emphasize that this is a theme that runs across all physics in 2025, the quest for understanding, the thrill of discovery, and the tangible impact that knowledge can have on technology and society. And I conclude this segment by telling the audience that the breakthroughs in new materials and condensed matter physics not only redefine what is possible in the laboratory, but also lay the foundation for the next generation of quantum technologies, energy-efficient systems, and devices that will shape our daily lives, connecting the microscopic quantum world with macroscopic applications. And that these discoveries, together with the cosmic, planetary, and quantum achievements of 2025, illustrate the remarkable breadth, depth, and interconnectedness of physics today, completing the final major topic in our journey before I offer a reflective closing message to the audience about the significance of all these breakthroughs and the spirit of discovery that drives science forward. As we reflect on the incredible discoveries of 2025, spanning the smallest scales of quantum materials to the most distant reaches of the universe, it becomes clear that physics is entering a new era of both precision and wonder. I want the audience to appreciate the unifying theme that emerges from all these breakthroughs: curiosity, meticulous observation, and the relentless pursuit of understanding. Because whether we examine the enigmatic little red dots at the edge of the universe, the subtle weakening of dark energy that could reshape the fate of everything, the dynamic processes deep within Earth's core, the transformative advances recognized by Nobel-level physics, the gravitational waves that allow us to listen to the cosmos, or the extraordinary new materials and condensed matter systems engineered at the atomic scale, the story is the same. Humanity is striving to uncover the rules of reality and apply them to enrich knowledge, technology, and our collective perspective. And I explain that each of these areas is remarkable on its own, but when viewed together, they reveal an interconnected web of discovery, demonstrating how the same principles of physics govern phenomena from the subatomic to the cosmic. And I narrate that in 2025, scientists have pushed boundaries not only in observation and experimentation, but also in computational modeling, theoretical understanding, and interdisciplinary collaboration, showing that modern physics is as much about teamwork, advanced instruments, and global cooperation as it is about insight and imagination. And I emphasize that this year, more than any, has shown us that the universe is both knowable and astonishingly complex, with surprises lurking at every scale, whether hidden in the core of our planet, encoded in the vibrations of space-time, or embedded in the behavior of matter under extreme quantum conditions. And I continue by saying that these discoveries also remind us of the iterative nature of science, where each breakthrough raises new questions even as it provides answers, and that the journey of discovery is ongoing, fueled by ever more precise measurements, innovative technologies, and the tireless curiosity of scientists across the globe. And I narrate that the implications of 2025's breakthroughs extend far beyond academia, influencing the technologies we will rely on in the coming decades, from quantum computing and advanced materials to energy-efficient systems and new ways of observing and understanding the cosmos. And I tell the audience that the pursuit of knowledge in physics is not isolated from human society, but deeply intertwined with our culture, economy, and vision for the future. Because understanding fundamental principles enables us to create tools, predict challenges, and expand the horizons of what is possible. And I explain that reflecting on the little red dots, we see how observations at the very edge of the observable universe can reshape our understanding of cosmic history, the formation of galaxies, and the forces that have shaped the universe since its earliest moments. And considering the weakening of dark energy, we recognize that even the grandest scales of space and time are dynamic and open to new interpretation, challenging our models and pushing us to imagine alternate futures for the cosmos. And I continue by emphasizing that Earth's core reminds us that profound complexity is not just out there in the stars, but also beneath our feet, where unseen forces generate the magnetic fields and geophysical processes that sustain life. And understanding these inner dynamics has both scientific and practical consequences, from navigation to planetary stability. And I narrate that Nobel-level physics breakthroughs of 2025 demonstrate the power of combining theory and experiment, revealing that insights into macroscopic quantum systems are opening doors to technologies that were once science fiction, while gravitational waves provide a new language to observe and comprehend the universe, transforming violent cosmic events into measurable signals that expand our understanding of matter, energy, and the laws of nature. And I explain that finally, the advances in condensed matter and new materials illustrate the human ability to manipulate matter at the smallest scales, creating phenomena and devices with applications that will touch every aspect of modern life, from computation and energy to sensing and communication. And I emphasize that taken together, these discoveries highlight a fundamental truth about physics, that the universe is unified by the same underlying laws, and that by exploring extremes, whether cosmic, planetary, or quantum, we gain insights that resonate across scales, inspiring innovation and deepening comprehension. And I narrate that 2025 has been exceptional not only for the quantity of discoveries, but for their quality, precision, and potential impact, showing that the frontier of human knowledge is ever expanding, and that our ability to observe, measure, and understand the natural world is limited only by our creativity and persistence. And I continue by saying that the common thread connecting all these breakthroughs is the human spirit of inquiry, the drive to ask why and how, the willingness to build instruments, gather data, and test ideas relentlessly. And that these efforts demonstrate that science is not static, but a living, evolving endeavor, constantly revealing new layers of complexity, beauty, and meaning. And I conclude this reflective segment by telling the audience that as we look back on 2025, we see a year in which physics not only answered long-standing questions, but also posed new ones, setting the stage for the discoveries of tomorrow, reminding us that curiosity is timeless, exploration is boundless, and the pursuit of understanding is a defining feature of humanity, encouraging each of us to remain engaged with the wonders of the universe and the possibilities of knowledge, because every observation, every experiment, and every idea contributes to the ongoing story of science, a story that is as exciting, mysterious, and inspiring as the cosmos itself. As we reach the conclusion of this journey through the remarkable physics breakthroughs of 2025, I want to speak directly to you, the audience, because understanding these discoveries is not just about absorbing facts, but about appreciating the extraordinary story of human curiosity and the pursuit of knowledge. And in my first-person voice, I want to remind you that the little red dots at the edge of the universe, the hints of weakening dark energy, the hidden dynamics of Earth's core, the Nobel Prize-level quantum advances, the gravitational waves echoing across space-time, and the revolutionary new materials and condensed matter systems are all milestones in a much larger adventure, one that spans the cosmos and reaches into the very fabric of matter. And I explain that each of these breakthroughs exemplifies the relentless drive to ask questions, to test theories, to measure with precision, and to seek answers in places both unimaginably distant and unimaginably small. And I emphasize that science, at its heart, is a story of discovery, one that is deeply human. And as I continue, I tell you that what makes 2025 special is not only the discoveries themselves, but the way they connect, showing us a universe that is dynamic, complex, and astonishingly beautiful, where the forces of nature operate across scales from the quantum to the cosmic, and where human ingenuity has developed the tools, both conceptual and technological, to perceive and interpret them. And I narrate that the overarching lesson from these advances is that our universe is both knowable and full of surprises, that what we observe today is just a fraction of reality, and that the next breakthrough may come from anywhere: a distant galaxy, a particle experiment, a deep Earth observation, or an unexpected property of a novel material. And I want the audience to feel the excitement that drives every physicist, the thrill of seeing the unseen, measuring the immeasurable, and understanding the seemingly unknowable. And I continue by saying that science is not static. It evolves, adapts, and grows with every experiment and observation. And in 2025, we have witnessed examples of this evolution on multiple fronts, from the smallest quanta to the vastest stretches of space-time, reminding us that learning never ends and that our quest to understand the universe is an ongoing story, one in which we are all participants, whether through curiosity, support, or engagement with the questions themselves. And I explain that what I hope you take away from these 2025 breakthroughs is not only knowledge of specific discoveries, but a deeper sense of wonder, an understanding of how the universe is interconnected, and an appreciation for the creativity, persistence, and collaboration that makes science possible. And as I speak, I emphasize that the scientists who made these breakthroughs are ordinary people driven by extraordinary curiosity, people who spent years, decades, or even lifetimes pushing the boundaries of what is known. And I tell the audience that in the same way, anyone with curiosity, patience, and imagination can participate in the adventure of discovery, because science is not reserved for the few. It is a human endeavor open to all who wish to explore, question, and understand. And I continue by reminding viewers that every observation, measurement, and insight contributes to a growing collective understanding of the universe, and that by engaging with science, you become part of that story,
helping to expand knowledge, inspire innovation, and perhaps even contribute to the breakthroughs of tomorrow. And I narrate that the year 2025 shows us that breakthroughs can occur in any domain, from cosmic phenomena to quantum systems, and that staying curious, asking questions, and exploring relentlessly are the keys to uncovering them. And I say that as we reflect on this remarkable year, it is also important to recognize the global effort behind these achievements, the collaboration of minds across continents, cultures, and disciplines, all united by the desire to understand reality. And I emphasize that this collective pursuit enriches humanity as a whole, connecting us to the universe in ways that are both intellectual and deeply emotional. Because the story of physics is also a story of human curiosity and creativity, and it reminds us that we are part of something larger than ourselves, a universe governed by elegant laws and surprising phenomena waiting to be discovered. And I tell viewers that the final takeaway from 2025 is both inspiring and actionable. Remain curious, stay engaged with the world around you, question what you think you know, and embrace the wonder of discovery. Because each of us, in our own way, can contribute to understanding, imagining, and shaping the future. And I conclude saying, so everyone, that was all. I hope you learned from what I explained. What type of topic do you want me to explore next? Mention it in the comments and subscribe to my channel so I can continue bringing knowledge and insights to you, because as we understand more, the world moves forward, and together we can continue to unlock the mysteries of the universe, one breakthrough at a time.